So we can consider every vector has some amount of x character and some amount of y character. So what I mean by that is if we look at these two lines here, you'll notice that neither one is, they're not equally in the x or in the y, right? Notice this red vector is way more in the x than it is in the y. This y vector, blue vector over here is way closer to the y-axis than it is to the x. I could say that this red line over here is more x, and I could say that this blue line over here is more y. So we can describe a diagonal line as having some amount of x character and some amount of y character, and we're going to call these components. Okay, this is really, really, really important because what we're going to do in physics is whenever we deal with a diagonal situation, we're going to make it a lot simpler by turning every single diagonal line into two straight lines. This is massive. Right? This is super, super, super useful because if we turn any diagonal measurement we get into two straight lines, we can greatly simplify the math we have to do in any situation by making everything one-dimensional. Any two-dimensional situation, we can just turn into two one-dimensional lines and then treat them separately like they're one-dimensional lines. That makes the math way easier. So whenever we have a vector that is moving diagonally, we're going to be able to give it, I need to get better at drawing straight lines, geez, an x component and a y component. And this will make a right triangle. So the y component tells me how much of this vector is acting in the y direction. The x component tells me how much of this vector is acting in the x direction. And these two straight lines, first of all, can be made out of any diagonal line, no matter what the angle is or what the situation is. If your line is diagonal, you'll always be able to do this. Second, and more important, this makes a right triangle, which we are going to be allowed to mathematically treat like it is a right triangle, meaning anything you can do to a right triangle, you can do to this. Okay? So we have some angle here. We're going to call that angle theta. Greek letter theta is used to represent angles in physics. And the names of my two lines here are going to be the name of my vector, subscript x, and the name of my vector, subscript y. So for instance, let's say that the name of my vector here is v. It's a velocity. I would call this measurement down here vx, and I would call this measurement up here v subscript y. So basically, all we have to do whenever we see a diagonal line, we kill it on sight by using trigonometry to turn it into two straight lines, and then we can use those two straight lines, like a right triangle, to determine what's happening in just the x direction and what's happening in just the y direction. By splitting those two things up, we can make doing the math a lot easier. Okay? So basically, we're going to do take all our diagonals, turn them into x and y components, do all the math for the x and all the math for the y separately, and that makes things a lot easier. Okay, so how do we do this? Very simple. We use the functions sine and cosine. You guys probably learned in trig. Okay, so, ka, toa. You probably learned this before. SOHCAHTOA is a way, it's a memory hook of remembering what the trig functions are. So basically, we have three functions, sine, cosine, and tangent. And we could say that sine is equal to, sine of an angle theta, is equal to opposite over hypotenuse. The cosine of an angle theta is equal to adjacent over hypotenuse. The tangent of an angle theta is equal to opposite over adjacent. On our right triangle, we have an x component, and a y component, and a vector I'm going to call v. Okay, so here we have SOHCAHTOA. We can, based on the angle we're looking at, use a different trig function to determine our components. So if my angle theta is here, cosine will be the adjacent side over the hypotenuse. The hypotenuse is this long one, which is going to be our vector. Adjacent and opposite are going to be determined on which line touches this angle. So the adjacent side touches the angle. So for instance, this x here is my adjacent side if I'm measuring this angle theta. If I'm measuring this angle up here, this y is my adjacent side. So your adjacent side is the one that touches the angle. Hopefully you're able to see what I mean by that. This angle, no matter which one it is, will touch both the hypotenuse and one of my other two sides, so the side that touches the angle is going to be our adjacent side. The one that doesn't is going to be the opposite side. So basically, based on where we're measuring our angle from, we can use the trig function to figure out what our x and our y components are. The classic situation is going to be like this. We measure our angle from the origin, from the ground, like this, meaning cosine of theta times the length of my vector v will give me my x component, and sine of theta times the length of my vector v will give me my y component. Okay? And this comes from using algebra to rearrange my trig identities over here. Right? If I'm solving for my opposite side, this one, it's going to be sine times hypotenuse. If I'm solving for my adjacent side, it's going to be cosine times hypotenuse. This adjacent side. So this is going to be the classic. You get your y component from the sine of the angle if it's measured from the origin times the vector, and then you get your x component from cosine times the vector. Now, here is the thing. The trig functions, sine and cosine, these are functions. So first things first, something I want to make clear. You will never use a theta in math by itself. If you have an angle theta, this thing will always go into a function like this, sine, cosine, or tangent. It will never, ever, ever get multiplied by itself. So this theta here, you'll only ever put that into a function because it is not a number. Sine and cosine basically convert an angle into a number by determining its fraction of being in the x or being in the y. So sine is a function that goes from 0 to 100% between 0 and 90 degrees, getting higher and higher and higher. Cosine does the opposite. It starts out at 100% at 0 and goes down to 0 at 90 degrees. So basically, if you were to add on a cosine and sine graph any point, those two spots together will equal 1. So like, for instance, this plus this, sine and cosine, those two points together will give you 100%. This point and this point, 100 and 0, this point and this point, 0 and 100. Basically, it's measuring the amount, the fraction of your line that is in the x direction versus in the y direction. And I'm going to throw it over to Live Action ASA to do a demonstration of this with a textbook and a marker. Okay, what's up, everybody? Live Action ASA here with a pretty simple demonstration. Basically, what we're going to be looking at here is how we can consider sine and cosine and their effects on a vector. So here I've got a physics book and I've got a dry erase marker. Notice right now, I would say that this book is at a 0 degree angle, right? So if you think for a minute, the fraction of gravity that is able to act on this marker is 0. The reason for this is because, obviously, this book is fully in the way. The force of the book is countering gravity. So at a 0 degree angle, 0% of gravity is able to work. And you'll notice that as I increase the angle of the book, I get a little bit more, a little bit more, a little bit more, a lot more, a lot more. And if I make the book go all the way up at 90 degrees, my marker doesn't even roll down the book anymore. It just falls straight down, right? So, in other words, we are starting at 0. As we increase the angle, a higher and higher and higher and higher and higher fraction of gravity gets to act. And at the top, the book is not interfering with the object's motion at all. So, effectively, we can say that at 0 degrees, the amount of gravity able to act on this marker is 0%. That amount gets higher and higher and higher and higher as we get closer and closer and closer and closer and closer to 90 degrees. Then, at 90 degrees, 100% of gravity gets to act. So you'll notice that, again, my marker doesn't even touch my book. It just goes straight down. It's as though the book isn't there, because at 90 degrees, it's not making any contact with the surface of the book. So, that is a way we can consider sine and cosine. We have a function that goes from 0% at 0 degrees to 100% at 90 degrees. And that we would call a sine function. Looking at this geometrically, we can determine that the sine of the angle is determining what fraction of gravity gets to act, which is why a sine of 0 gives us none, a sine of a low angle gives us a small amount of gravity, sine of a high angle gives us a lot of gravity, and sine of 90 gives us all of gravity. Okay, Live Action ASA out. Thanks, Live Action ASA. Okay, so let's all really quick do an example of this. I'd like you guys to try to split these following two vectors into their x and y components. So let's say we have a boulder being rolled downhill at an angle of 45 degrees. Gravity is causing it to accelerate at a rate of 5.4 meters per second squared. What is its acceleration in the x direction, and what is its acceleration in the y direction? So we want the x and y components of gravity, okay? And then the second part is an archer fires an arrow upwards at a 31 degree angle from the ground with a velocity of 19 meters per second. So please pause the video right now and try to determine what the x and y components of these numbers will be. So go ahead and give that a shot. Pause the video right now, and we'll come back in a minute. Okay, let's try to solve this. So, I have a slope like this. This is 45 degrees. And I've got a boulder. It's rolling. Got an acceleration of 5.4, excuse me. 5.4 meters per second squared. Okay? And I want to know my x and my y components of that acceleration. Well, all right. So my x component, or my y component, I'll draw that one first, is going to be like this. And my x component is going to be like this. Let me draw my arrow a little bit better, actually. There we go. So that's my a. Here is my ax. Here is my ay. Okay, so the hypotenuse of this triangle is 5.4. My angle theta is 45. The adjacent side to that is going to be the x. The opposite side to this 45 is going to be my y component, okay? So I can say that the sine of 45 degrees times the length of my total vector, which is 5.4, equals my acceleration in y. And I could say that the cosine of my angle 45 degrees times the length of my total vector 5.4 equals my acceleration in the x direction, right? Cosine times your vector will give you the adjacent side, the touching side of your angle. Sine of that angle will give you the opposite side. Okay, cool. So let's go ahead and do that. Sine 45 in a calculator comes out to be about 0.707 times 5.4, comes out to be like 3.82. And x comes out, cosine of 45 degrees comes out to be 0.707 times 5.4, and that is about 3.82 as well. Okay, so, interesting. Notice my y and my x component in this case are exactly the same. And you might be wondering, why are they exactly the same? Well, this is a 45-degree angle. Remember earlier I said that sine and cosine represent a fraction, right? Specifically, they represent the square of the percentage, right? So, the square root of the percentage. So basically, 0.707, that is the square root of 0.5, my friends. So effectively what this means is that sine and cosine of 45 degrees are going to be the same number because this is exactly the middle between being 0 and being 90 degrees. So in that question, both of our sides are 3.82 and 3.82. The only thing we have to add is a direction. So the y direction is going down. So I would add down to this. The x direction is going to the right. So I would add right to this. All right, perfect. Let's go ahead and take a look at the next one. Here you've got an archer shooting an arrow upwards at a 31-degree angle formed with the ground. Velocity is 19 meters per second. So we have 31 degrees measured from the ground. Velocity is 19 meters per second, like this, okay? We got to find our x and our y components. Okay, so like usual, our x component is going to be the horizontal line in the x direction. Call that vx. Our y component is going to be the vertical line. Call that one vy. Okay, so remember, the side that touches gets cosine. That's the shortcut that I like to use. Cosine is the adjacent over the hypotenuse. So the x side is touching this angle 31. So we get cosine 31 times our vector's length. And that will give us 0.86 thereabouts times 19, which comes out to 60.3. I'm going to round to one decimal place here. So Vx equals 16.3. And then for my y, it's the opposite side, so it's going to get sine. Sine 31 times 19. Sine of 31 degrees is going to be 0.52. Again, I'm rounding to the nearest, I'm rounding 2 decimal places here. Times 19 is going to be about 9.8. These are both velocities, by the way, so their units are going to be the same as our big vector. So that's meters per second. This one over here is also meters per second. And then lastly, we just have to add a direction to these two. So my x component is going to the right, and my y component is going up. Now, one last thing I want to mention, for your trig functions, right here, it's important that you make sure your calculator is in degrees. Some calculators default to being in radians. If I gave you if I gave you an angle in degrees and your calculator spits out a weird number, like a negative number or something, make double sure your calculator is in degrees and not radians, because degrees and radians are different units. You'll end up getting different answers for this. So here in Physics 1110, we're going to be measuring most of our angles in degrees. So just make sure that your calculator is not in radians to avoid that happening. But anyway, that's how you break an angle or a vector into components. Not so bad.